Hello. So, a tale of two very different secure ICS architectures. So what is a secure ICS architecture? Well, you all know the Purdue model. And you might remember the S4x19 panel is the Purdue model dead. Some people thought it was still accurate today, and others thought it was not relevant anymore, especially when considering cloud. Traditionally, there has been a rigidity to what a secure architecture is. And here is an example of rigidity, the DMZ. Imagine you need a new interconnection with your ICS. Well, it's simple. Put a proxy server in the DMZ and only allow incoming communications to the DMZ. It used to work, but does it still make sense today? Well, maybe not in all cases. And so let's see how we can think about the future of ICS architecture, having in mind this year's S4 motto, no limits. And so let's take an example. I've been working for various companies that have a large variety of control systems. First, historical businesses, such as power plants, nuclear, chemical, or refineries. But also new businesses, such as solar and wind farm. These various businesses can now be found within the same company. For these companies, the existing ICS cybersecurity policy needs to be adapted to new usages and businesses. So for these companies, how can we define cybersecurity requirements and rules that would apply to the entire company? In this presentation, we will compare and contrast the requirements and corresponding secure ICS architectures of two different businesses within the same company. But first, an assumption. To narrow the discussion, I will only discuss command and control systems, so no monitoring and no safety systems. And now let's deep dive in our two use cases. So first, the historical business, so power plant and refinery. So here we usually have big plants on a single geographical location with many people working on site. These systems are designed to operate locally, so on a single geographical location, and autonomously. There is only a few interconnections, and they are usually not essential to the industrial process itself. There is a high volume of assets on the network and pretty standard industrial assets. And the industrial process is usually complex, with a lot of command and control requests. Now, the new business, the solar and wind farm use case. Here we have industrial sites that are geographically distributed and that are communicating through the internet. So we can find IIoT, command and control operated from external partners or even from the cloud. There is a lot of small sites without any human presence and a few assets on the network. We usually have data loggers and inverters, mainly on these networks. These systems are also operated from the cloud. So from a command and control perspective, there is only a few operations possible, and it's mainly start and stop. And these systems are also about energy management and optimization. The idea is to gather data and optimize energy production. So would you have the same architecture and cybersecurity requirements for both cases? Probably not. So let's start with the historical ICS secure architecture. So here we have a pretty standard ICS architecture following the Purdue model. So we have an industrial site with a dedicated OT network on a single geographical location. And so here we find standard assets such as the SCADA servers, the workstations, the PLCs, sensors, actuators. And this OT network needs to communicate with the IT network. And so we do that through a DMZ with two firewalls. One firewall between the OT network and the DMZ, and one firewall between the DMZ and the IT network. And here, we do not have any direct communications between the IT network and the OT network. Everything goes through the DMZ. And what do we have in this DMZ? Well, we have a Bastion server for remote access, for example. We have update server, antivirus servers, and we also can have some file servers or other application servers. Then what do we have next in this architecture? We probably have a wide area network for the company connected to the company network data center. And here in the data center, we may have a central services DMZ, and also the main and probably the only internet gateway. So actually, the remote access goes through this. So the remote workstation will connect to the VPN of the company, then access the first bastion server in the data center, and finally get to the industrial site, first on the bastion server, and finally accessing OT assets on the network. So what are the key requirements for this architecture? Well, we have a DMZ between the IT and the OT network, protected by firewalls, and so 2 firewalls, like I said earlier. Second point, we have no direct communication between the IT and the OT networks. Everything goes through the DMZ. Third, we have a protocol break in the DMZ with relay servers of proxy. And fourth point, there is no local internet access on the OT network. We have to go through the IT network to go out on the internet. So would this architecture work with our solar and wind farm use case? So first, let's try to apply the same architecture principle to this second use case. So we still have our OT network on the main operator site. However, here we only have workstations and engineering workstations on this operator site. The industrial process is actually elsewhere. But then what do we have? So the DMZ, the IT network, the company network data center, and so still the remote access. But where is the rest of the industrial process? So we have industrial sites with OT network and only small assets on this network. But how can we interconnect these sites with our main operator site? And maybe a constraint here to start. So actually, we wanted to implement MPLS for this network. However, we met with telecom operators, and they said that it was not technically feasible to implement MPLS on 20% of the sites due to geographical constraints. So here, we have to use the internet to interconnect the sites. So if we follow our previous architecture principles, what do we have? So we have a DMZ. We have a first firewall between the OT network and the DMZ. We have a second firewall or router between the DMZ and the internet. Since we need to communicate with the main operator site, but the only internet access is the company network data center, we will have VPN IPsec tunnels between these industrial sites and our data center. We are not allowed to have any direct communications, so we have relay servers in our DMZ. So here, to make the industrial sites communicate with the main operator site, we go through the whole IT network of the company. And then what do we have next? Because I haven't forgotten the SCADA servers. They are hosted in the cloud, in an infrastructure as a service. And here, similar constraints. So the first DMZ, the first firewall, the second firewall, the VPN IPsec tunnel, the proxy server. But does this architecture really work? And let's take an example with the most bus flow, for example, between the main operator site with the operator workstations and the PLCs, or the SCADA servers with the PLCs. Well, here we go through the whole IT network to make these sites communicate with each other. Actually, can we really implement a proxy in the DMZ, or shouldn't we authorize a direct communication between these industrial sites and the main site? And you may have noticed that there is a lot of DMZs and firewalls in this architecture. And for the small industrial sites, so we have 2 firewalls per site. And actually, it might be feasible if we only have a couple of sites, but imagine you need to interconnect 300 industrial sites. Well, it does not scale, and it seems a bit too much for this architecture. So let's try something else. So what could we build and implement that would still be considered as a secure architecture for our solar and wind farm use case? So like I said, many different OT networks and these industrial sites that are geographically distributed. We have our main operator site with only workstations. We have our industrial sites with no human presence and only a couple of assets on the network. And we have the SCADA servers hosting in the cloud. And these sites need to use the internet as a transport means to communicate with each other. So what can we have here? And one secure solution would be to implement and virtually create a wide area network leveraging SD-WAN technology. But remember our meeting with the telecom operators earlier? Well, it's them who recommended to implement SD-WAN in this architecture. But what is SD-WAN? Software-defined wide area network. So here you virtually create your wide area network with a network of VPN tunnels over any physical network. So this way you can have very different physical network, like public internet, different operator networks, radio, and still build your WAN using logical segmentation. So what do we have here? So we will have SD-WAN edges at each location with embedded next-generation firewalls, and we will build VPN tunnels between each of the locations. So we will communicate the main operator site with the industrial sites, and the cloud communicate with the industrial sites. However, the industrial sites themselves won't be connected to each other, but because there is no real need of communication between these industrial sites. And within these VPN tunnels, we will implement network filtering to only allow legitimate communications, so the Modbus flow, for example. And we can also add detection by activating IDS functionalities on these SD-WAN edges. But where is the rest of the architecture? So we still have a DMZ, but here we have a DMZ between the OT network and the internet directly. So we do not go through the IT network anymore. And what do we have in this OT DMZ? We have different zones protected by different firewalls. We have the central services DMZ and the external DMZ. So the remote access will go through here again. So we have the remote workstation that will connect to the global OT VPN, then access the Bastion server on the central services DMZ, and finally be able to connect directly to the industrial assets through the SD-WAN architecture and network. And what do we have also in the central services DMZ? Still the updates and antivirus server. And here, these servers will get their updates directly from the internet through URL whitelisting, through proxies, for example, on the external DMZ. And then these servers will distribute their updates directly on the OT network through the SD-WAN architecture. And imagine in this architecture, you need to interconnect external partners, for example, or external clouds. Well, you can have additional flow controls and analysis with relays and proxies, for example, for standard protocols such as HTTPS or SFTP. And you can also have a network probe for industrial protocols. But where is the IT network in this architecture? Because we still need to have interconnection with the IT network. However, the interconnection won't be at the main operator site level. The interconnection will be done directly through the cloud with a dedicated firewall between the central OT DMZ and the IT network. And we probably have another one network to interconnect the sites with the cloud for the IT network. So what are the differences with this architecture and the previous one? Well, here we have OT communications that are not going through the IT network anymore. We have a DMZ between the OT network and the internet directly, and we only have one global DMZ for the OT network. So what are the key requirements for this architecture? First, we have the VPN IPsec tunnels between the industrial sites that are communicating through the internet. And in this architecture, we are using SD-WAN technology. Second point, we have a global DMZ between the OT network and the internet. So we do not go through the IT network anymore. Third point, we have firewalls with restricted firewall rules. And so we have firewalls at each location of the OT network. We have firewalls in the OT DMZ, and we have firewalls to protect the internet and the IT network. And fourth point, we have a network probe in the DMZ for flows analysis, and especially for flows that cannot be proxified and have relays or proxy. So to sum up this architecture here for the solar and wind farm use case, we have a multi-connectivity using the internet. We are leveraging SD-WAN technology to create a fully distributed industrial network over the internet with a large cloud strategy. And we adapt the Purdue model and place the components based on their functionality and not where they are geographically in the network. Because the internet tends to be represented as a level 5, which is not really accurate, and especially in this case. However, be careful, because this architecture is actually riskier than the historical one. And maintaining a good cybersecurity level is difficult. And drifts can be observed over time, especially with SD-WAN. For example, with the misconfiguration of one of the SD-WAN edge, we could completely expose one of the industrial sites directly on the internet. So here we have several requirements that need to be respected to protect the industrial assets. First, we need to control the communications from end to end. And the communications need to be secured based on their level and the business need. So for example, the VPN tunnel, the network filtering, and based on the use cases, we can have also relays, authentication and encryption for the communication, as well as detection. And actually, in this architecture, rigor is key. And what I like also about this architecture is that cybersecurity basics will need to be respected finally. But now, how can we define cybersecurity requirements and differentiate these ICS secure architectures? And we are still working on the same company. So actually, this architecture for the solar and wind farm case can be considered as a secure one. However, it might be too risky for the power plant use case. And earlier, we said that the historical architecture would be a bit too much for the solar and wind farm use case. So maybe can we build something around risks? So let's try to build an ICS classification methodology. So here the goal would be to classify our industrial systems and not the industrial sites completely, because there can be many different industrial control systems within the same industrial site. So here we will try to put our industrial control systems on a risk matrix and try to differentiate their criticality. So actually, we use a risk-based approach following the ISO 27K. And in my case, I took the ANSSI, which is the French National Security Agency, ICS classification methodology as a base, and I adapted it to the context. So I won't detail the whole methodology, but only give you the main points. So first, we have the impact. So here we use the company global HEC impact scale, and it needs to be adapted to all businesses within the company. So we have an impact scale on several types of consequences, like environment, human, image, financial. And the global impact will be the maximum rated impact by consequence. Then we have the likelihood, and here we can have several factors that can be considered. First, the attacker's level. Are we talking about a non-targeted attack? Are we talking about a private organization or even a state organization? Then we have the functionality. So here, are we talking about a monitoring system, a command and control system, or a safety system? Then we can consider the connectivity. Am I talking about an isolated network? Am I interconnected with a corporate network? Do I have a distributed network using a public network or a private network? And another factor to consider would be the level of access control. So here we are talking about identification, authentication, and access control. So for each of these factors, we will get a number, and then we have a formula to get the final likelihood. And then with the impact and likelihood, we can put our ICS on a risk matrix that will give us the classification of the ICS. And in this case, we have 4 classes of ICS possible. And something important, do not forget to consider regulation, because you may have ICS classification, a minimum for certain control systems, so if you consider, for example, critical infrastructures. So let's try this classification with our 2 use cases example. So first, we consider the impact. So for the power plant or refinery business case, here we have a high impact because we have high HEC risks. So we will probably have an impact 3. However, for the solar and wind farm use case, here there is no HEC risk, and actually we cannot do much remotely besides just starting or stopping the production. So actually here the highest impact will be financial due to the loss of production. So here probably an impact 2. Then for the likelihood, to make the case easier here, we will consider the same functionalities, the same attacker level, and the same access control. So it's the connectivity that will make the difference. So here, for the power plant and refinery, we have a low connectivity because we have an industrial network on a single geographical location, and there is only a few interconnections with the IT network. So with the formula, we will get a likelihood of 2. But for the solar and wind farm, we have a high connectivity because we have geographically distributed industrial sites that are communicating through a public network. So with the formula, we will get a likelihood 3. So in terms of classification, we end up with a class 3 system for the power plant and refinery and a class 2 system for the solar and wind farm. So we have a different classification for our 2 use cases. And so we can have different cybersecurity requirements for the different classifications. So for example, for class 3 system, we could make mandatory to use MPLS for distributed network. We could forbid the use of cloud and external partners performing command and control on their systems. And however, for class 2, we could allow the use of public network, having VPN tunnels and network filtering, and we could allow command and control from the cloud, having VPN tunnels as well, but also detection and network probe, for example. But can it be sensible? Well, unfortunately, no. So let's take a step back on our example. What was the main decision factor for the secure architecture? It was connectivity and impact. Because for our power plant and refinery, we have high HEC risk, and so we do not want to have a lot of interconnections. But for our solar and wind farm use case, there is not a lot of HEC risk, and we can allow to have multi-connectivity using the internet, for example. But can we use additional factors, and can additional factors be considered to help with the classification and requirements? Well, yes, we can consider, for example, multiple expositions. Because in this presentation, I talked a lot about cloud interconnections. But we can also consider interconnections with applications on the corporate network, for example. And here we need to consider and to consider the system as a whole and consider the implications of interconnection for the whole system. And for example, I talked a lot about the central services OT-DMZ. But here, since we are talking about the same company, do you think we can mutualize the same zone for our 2 examples? Or is the risk of compromising our power plant through the solar and wind farm is too high? And you can also have other factors to consider, regulations, like I said earlier, but also physical access. And if you talk about IoT, you can also talk about device access control and data confidentiality. But in the end, be pragmatic and do not stick to a formula. You need to consider key factors and make your classification accordingly. And so one idea could be to build architecture patterns. So you can identify several use cases for your company and build reference architecture based on risk analysis. And this will need to be maintained regularly as business needs and technical capabilities evolve regularly. So here the idea would be to respect global cybersecurity requirements for your ICS depending on your classification. But then for the detailed implementation, you can use the architecture patterns as a guide and build adapted architecture for each of your new use case. So now takeaways for the presentation. So we've seen that control systems can be very different, and thus the security rules and architectures can be different. So we've seen that the historical ICS secure architecture is not applicable to the new usages and that the Purdue model needs to be adapted. But what are the key factors to have in mind for an architecture decision? Well, First, what does the control system do, and what are the business needs? Then, what would be the impact, and especially in terms of HEC? And third, what is my level of exposition for my system, especially in terms of transport means, but also in terms of applications and other systems connected to these applications. So the idea would be to document concrete use cases for your company, because it will help in your classification and architecture decision. And so I would recommend to consider launching a task force to support your projects and build secure architectures for new ICS usages. And the final thought, how can we find the right balance? Because having different secure architectures is good for each of your new use cases, but only up to a certain level of manageability, because you will need to manage these solutions and architectures within your company. So unfortunately, you cannot have as many architectures as control systems. Thank you for your attention.